All right, welcome everyone to this week's Autonomy Talk. This week is a great pleasure to have with us Professor Anastasia Bizyaeva, who is an assistant professor in the Sibley School of Mechanical and Aerospace Engineering at Cornell University. And there she leads the Control and Computation for Complex Systems group. So many of you might know Anastasia, but I'll give you a very brief introduction. So she holds a bachelor in physics with a minor in mechanical engineering from UC Berkeley. She then moved to the other coast, the better coast, I would say, where she received a PhD in mechanical and aerospace engineering from Princeton in 2022, where her dissertation also was awarded a award for excellence. And before joining Cornell, actually, she was still undecided between the two coasts, so she spent some time on the other coast again at the University of Washington as a postdoctoral scholar with the NSF AI Institute in Dynamic Systems. And then, of course, she decided for the good coast and she came back to Cornell. Her research is very exciting, explores mathematical connections between collectively intelligent behavior, but also biological and socio-cognitive systems. And she applies these things to the design of autonomous and artificial intelligence behaviors in engineering teams. And today she's going to talk about bifurcation-guided control of fast and flexible decisions in individual and collectives. So she said it's fine to ask questions during the talk. So if you have a question at any point, feel free to write in the chat or raise your hand and I'll give you the word. I'm very happy to have Anastasia here. So without further ado, the stage is yours. Thanks so much for coming.
Great. Yeah, thanks a lot. Can you hear me okay? Great. Yeah, thanks a lot for the introduction. Thank you for the invitation. I'm really excited to speak to this group today. If I don't notice the chat, please shout out. Sometimes I'm not very good at monitoring that when I'm speaking. But so I'm excited to talk with you today about a topic that I've been thinking long and hard about ever since my PhD, and that is how bifurcation theory is actually really useful for control and coordination. And so today you'll hear about a bunch of different work that I've done in this area, both with collaborators and now even with my own student here at Cornell. And so before I get into the meat of this talk, I just want to upfront acknowledge all of the contributors to the things I'm going to talk about. Naomi Leonard from Princeton, Alessio Franci from University of Liège, who really set me on this path of thinking about bifurcations and control and how the two can synthesize. Collaborators, Tyler Payne and Michael Benjamin at MIT, whose work you'll hear about towards the end of the talk, and my student Shui Wang here at Cornell, as well as Eduardo and Amanda at Cambridge, who are collaborating with us on some of the things I'll talk about. Anyways, I think research is always a team sport. So I want to thank upfront everybody who's contributed to everything that I'm going to talk about. And so what is this talk actually about? So all the things I think about are really grounded in problems of autonomy and coordination, and thinking about the rise of deployment of autonomy across different industries, from transportation to warehouse and delivery work to the energy sector to agriculture to smart sensing, smart grids, things like that. And so we're living in a world where that's now inhabited by many different multi-agent systems that need to make more and more complicated decisions together. And decentralization is inevitable, because at scale, doing all of this in a completely centralized way becomes infeasible. And so a lot of what I think about is how can we actually enable local decisions that can give rise to collective properties in systems. In other words, how can we design collective intelligence that makes our systems resilient, robust, adaptive as they operate autonomously in the real world or with us. And so I already used the word decision a couple of times, and it was in my title. And so I just want to clarify a little bit what I mean by decision making, and at least in the context of this talk. And why is it interesting? Well, decision making, as I define it right now, is going to be on making a choice or a ranking among some discrete set of options. That could be a set of actions one must take, a set of velocities to choose among, etc. And these types of discrete decisions are, I would argue, a really core building block of pretty much all autonomy, right? Because we oftentimes work with discretized spaces, and a lot of tasks can be abstracted out to a type of discrete set decision. So anything from choosing an object to grasp among many with a robotic arm, or choosing a leader in a group collaboratively, or choosing a waypoint to navigate among multiple options, but also things that are a bit more heterogeneous. So problems in allocation and scheduling. Oops, I just realized this did not cover me over, but when it comes to decision making, the thing that really motivates the rest of this work is that the most difficult decision that one can make is actually one where there's no clear best choice of option. And we deal with these kinds of decisions all the time. As human beings, we go to the grocery store and there's many completely identical alternatives, like these bottles of oil, or we navigate through space, and sometimes there's multiple doors that lead to the same seminar room, right? But these kinds of decisions that are among identical or near identical options, these are exactly the type of pathological examples that autonomous systems often freeze up on, right? Because this type of redundancy and how valuable a particular option is a type of symmetry. And we oftentimes struggle with symmetry-induced deadlocks and indecisions when it comes to autonomous systems. And so I'll give you a couple of simple examples just to illustrate what I mean. So here I'm showing you a very, very simple setup where there is a point mass agent, and you're looking at a top-down view of a room, and the agent has a goal, which is to move towards one of the two targets, which are the gray circles. And this goal is attempted using one of two control strategies. So on the left, we have a model predictive control that is attempting to minimize distance to the goal targets, agnostic to which one it should choose a priori. And on the right, we have a potential function type approach that is also quite popular in robotics and is known to suffer from some of these issues with local minima. And as you can see, so the blue and the green lines, these are ensembles of actual physical trajectories through space that the agent took in these using these two control strategies, and you can see that it has clearly failed to actually achieve its goal, which is reach one of the waypoints, because of this symmetry in how the targets are arranged in space with respect to its starting location. So in both of these strategies, the agent got stuck in indecision because of again, this type of asymmetric configuration. Then we have also indecision that happens in multi-agent settings. So this is the video on the screen here is a really common example of a deadlock that might happen when you have a multi-agent team with conflicting objectives. In this case, you have a group of robots with navigational goals to just go to a waypoint that's directly across from them in the room. And they have some sort of a safety filter implemented on board. And you can see that despite there being a safety filter on board, the robots fail to commit to a decision of do you go left or do you go right to avoid collision, because in fact there's somebody on the left and on the right, and you end up freezing up the whole system and causing a traffic jam This is known as the freezing robot problem, and often happens with various different safety filters that we use. And then the other component of autonomy that really motivates me to think about is that we often operate in dynamic environments. And so autonomous agents not only need to be able to select a good choice when one is available, but also they need to be able to resolve indecision when it's costly. But also they need to be able to adapt, and they need to be able to adapt quickly when something changes, right? There's a change in mission parameters that maybe comes from a human collaborator input, or something changes about team composition, somebody's battery dies, and there's an urgent need to send a different team member to take over a task. Or there's something happening in the environment, like the weather changes or a fire starts. So it is not only important to reach individual or collective decision during operation, but it is also important to adapt it to changes and do it quickly. A huge inspiration for a lot of what I do comes actually from thinking about, well, how does nature solve the same problem? Because there's actually a lot of examples in social systems, in biological groups, and in cognitive systems of decision-making that is very fast and flexible, in which groups and individuals are able to overcome the type of symmetries that tend to freeze up our robotic systems or autonomous systems, but are also able to simultaneously commit to a good choice when there is one. So here I'm showing 3 different examples of systems that accomplish this type of symmetry breaking. They're a very different system from the get-go. So one of them is a very canonical system, the honeybee nest site selection problem. So house hunting honeybees go out and they look for nest sites, they judge their quality, and there's a whole body of really beautiful work in biology about how they evaluate these differences in quality and how they make that collective decision to go to one of the sites that they found. It is one of the most remarkable things about the honeybees that, in fact, when they're presented with equally valued alternatives, they don't get stuck and do, in fact, commit to a decision and break a social deadlock. And there's a lot of amazing modeling that's done in this space, trying to understand how do they accomplish this, what strategies do they use. But another place we see symmetry breaking, so on the right here, you see, this is from another recent paper led by Vivek Shridhar on geometry of decision-making in individuals and collectives, where they looked at what are the paths that animals take through space when they have to make decisions between different options, for example, food sources that are placed. And so you can see here traces. So the heat maps are of experimental traces. This is a figure from the paper cited in the slide, where you see that these animals, so in this case, I think it's fruit flies and locusts, they are able to, in fact, handle a very similar scenario to the one on the previous slide, where we saw both like the NPC strategy and the potential function strategy freeze up. Animals actually are able to commit to a choice in this symmetric configuration. In fact, the choice is pretty binary. And what you see from left to right is that when animals are far from a target, they tend to go towards the average of the 2 target locations. So for the first part of their path, they seem to be uncommitted, but then there's a critical threshold in the visual angle between the 2 targets, after which they go to one or the other. And you see similar things in cognitive circuits that that they're or cognitive circuit models that are used to describe more high-level decision-making in human brains, things like switching between tasks based on perceptual cues, where we can, in fact, switch from one task to another. And it's often described in terms of these potential landscapes and how they're shaped and reshaped by stimuli. And so what is in common between all of these three systems that I showed you? Well, one thing is that they all solve a similar problem. They are able to integrate evidence into their decision process, make good decisions, but also break symmetries. But also, when these systems have been modeled, we can understand these decisions as the outcome of a dynamic nonlinear evidence accumulation process, where some sort of a decision state is updated in a way that depends also on a bias. So in this case, when I'm talking about a decision state and a bias, the distinction is the bias is related to the observation of how good are the options. So this could be some estimate of the quality, some external input saying, hey, go to the option 1 over option 2, or prior knowledge or predisposition about these options. And the decision state is a dynamic state that is updated based on which the actual decision is going to be made. So it's influenced by the bias, it's influenced by the information, but it's not equivalent to the information. And so oftentimes we refer to this as a belief or an opinion when it's something abstract. In models of specific processes like the ones on the previous slide, this decision state might be some sort of a firing rate of a neural group that's integrating evidence towards different options or different actions, or proportion of committed individuals in a group that is selecting one option over the other. And so from this dynamical systems point of view, how the decision is made in all of these different qualitatively different systems from the previous slide can be explained basically using the same diagram. And so this is a bifurcation diagram. I'm showing it on the slide here. So on the vertical axis, we have that decision state, and the blue and red lines represent equilibria of this state, so where trajectories will converge over time, where on the horizontal axis, you have some sort of a relevant parameter, which reflects, for example, an urgency of the decision. How important is it to make a decision soon? And this parameter, we assume for the sake of this diagram, is static, but to spoil the message ahead, we often think of it as something that can be dynamic and adaptive, and in fact, that is how flexibility and sensitivity in these systems often arises. So in this case, what you see is when this parameter, which you can roughly think of as urgency of the decision, is low, you have a state of indecision that is globally stable. And you see that, for example, in the trajectories of the animals that were moving towards targets. In that case, indecision might have been a state of compromise, where you're just choosing to average the two targets, you're not committing to either one. And then when the parameter P crosses a threshold, that's our bifurcation point, that's dedicated with this gray vertical line here. That bifurcation point causes the states of indecision to become unstable. And so now there's two new equilibria, which are these global decision states, 1 and 2, at which now the individual of the group commits to some configuration of beliefs that is non-neutral, that rejects an alternative. But the other thing that's really interesting is what happens when you have information. So the left picture corresponds to the uninformed case, when there is no bias, or when there is no perceived difference between option quality. On the right-hand side is what happens in these types of systems when there is a preference towards one of the options based on some observation input or predisposition. And that's in the dynamical systems language, this is can be understood as an unfolding of this bifurcation diagram. And that just means that near the bifurcation point, the picture breaks up. And it, in fact, breaks up in a direction that favors the option that is selected by the bias. And so these bifurcation points, they are points at which dynamical systems are structurally unstable, which means even small perturbations cause major changes in the topology of their bifurcation diagram. So, in other words, if a system is operating close to this bifurcation point, it can be ultrasensitive to even very, very small biases or quality differences, for example, between options. And so it can respond to very, very small signals. So across all of these biological systems, you see that this structure of decisions organized by bifurcations is core to what enables them to have these nice properties of being both value sensitive and able to break indecision when necessary. And so our approach in this space is to take this insight from biological decision makers about how to design the decision logic and apply it to autonomy. And so we model these multi-alternative decisions as a dynamic nonlinear evidence accumulation process in which we can then classify rigorously the decision states that will emerge and how they depend on relevant quantities like network structure, attention, incoming biases or information. And the ultimate goal is to use this type of framework as a tractable building block for autonomy that allows us to actually incorporate these symmetry-breaking mechanisms into various mechanisms for autonomous decision-making and especially multi-agent coordination. And so the big picture takeaway from all of our modeling work and what the message we're really trying to put forward with this is that these fast, flexible, tunably sensitive decisions, both in individuals and collectives, they're organized by bifurcations, controlled through feedbacks, and modulated by network structure. And so in the rest of this talk, I'm going to first go into a little bit of the nonlinear opinion dynamics modeling framework that we've developed with some citations on this slide that captures some of these like minimally complex components of the symmetry breaking process. And then I'll give two examples of how we've applied these ideas to practical scenarios in both single agent and multi-agent autonomy. So, and so the first part of this is based on a body of work that we've done in close collaboration with Naomi Leonard at Princeton and Alessia Franci at the University of Liège. And so now I'll describe to you this modeling framework. And so in particular, I'll start by talking about a binary decision that's made by a single agent. So I'm going to assign a scalar real-valued belief to agent I, and it's going to be informed by this bias I, which I already described to you as a quality estimate. And so in this binary setting, you can think of beliefs and biases. When they're positive, then they're favoring decision 1 or option 1. And when they're negative, they're favoring decision 2 or option 2. Then we can design a very simple dynamic belief update rule, which is grounded in its form in models of cognitive circuits and Hopfield networks and similar nonlinear models of distributed information processing. And so we model this belief update as an ordinary differential equation in which an agent is integrating the bias, which is that information about option quality, and at the same time, the bias is competing with a self-excitation term here. And so this self-excitation term is really important. So S is a saturating function, and U is just a parameter. So when U equals 0, then at equilibrium, the belief of the agent is equal exactly to the bias. So it reflects perfectly this quality estimate that we have. And U is a parameter we refer to as attention, and it reflects the urgency of the decision, or how much the agent in this single agent case is self-reinforcing their own belief. And so so the attention you can think of as a quantity that modulates the relative importance of the influence of internal external states versus evidence about the option quality. And this very, very simple model, again, this is just a saturating nonlinearity, it's locally linear, but it captures exactly the picture that I showed you on the previous slides of this organizing principle of these symmetry-breaking decisions. So when attention is low, this model in the unbiased case on the left leads to a state of indecision, whereas the belief converges to 0. And for a large attention value, you get a symmetry breaking and an agent commits to a decision. And of course, we also recover this sensitivity to bias on that I'm showing on the right. So when the agent is informed that option 1 is better, then near the bifurcation point, it actually becomes extremely sensitive to that quality. And so one of the things that we might want to take away from this, from a point of view of design, is to make a decision is to transition from a point of indecision to a point of commitment. In other words, it's with respect to these bifurcation diagrams, it's a movement from left to right, right? And so what we really want to move towards is not to think about this attention as a static parameter where it defines a single operating point on this diagram, but rather we might want to think about evolving it through local feedbacks so that an agent in a state of indecision might be able to visit this sensitive region in the middle, pick up the information that the bias is providing and amplify it towards a much more strong nonlinear decision state. And a big part of these frameworks that we're proposing is exactly that, is a way to design these nonlinear feedbacks in order to trigger these types of transitions. So here I'm showing a very simple mechanism for for dynamic attention, where the agent is updating its attention proportionally to the square of its opinion or belief. So in other words, if its belief becomes sufficiently strong, the attention starts riling up. So the urgency also gets stronger. I think there's a raised hand.
Yeah, so there's a question from Kathy, I think.
Yeah.
Hi, Anastasia. I got one quick question. So how does this bifurcation behavior relies on the shape or the specific form of the SZ? Is it like as long as you have this type of platoning and monotonic behavior, then you can observe something like this?
Yeah, exactly. So the only so for the bifurcation analysis, to characterize the local bifurcation diagram, you just need these two assumptions. and also some non-degeneracy assumptions. So the second the first derivative we're just normalizing to 1, and the second derivative it should be 0. So oftentimes we'll assume that the saturating function is odd, but in general you get a picture similar to this for a pretty wide range of these saturations. So even if you have like a quadratic term, it just perturbs the diagram a little bit.
Oh, interesting.
If it's small.
Thank you.
Yeah. I think
And there's also a question from Grant in the chat. Do
Yeah.
you assume that you know roughly the symmetric decision to make? For instance, the number of symmetric options, the position, so on?
Yeah, so in the baseline framework, yes, you assume that that's the case, but actually in one of the applications that I'll show you towards the end, where we're doing vision-based navigation towards in multi-target settings, I'll show you an example of how you can use this type of mechanism agnostic of how many options you have. Yeah, but yeah, that's a good point in all of this. At first, we are assuming that we know exactly the number of options. Yeah, thanks for the question. Yeah. But anyhow, so back to this story. So where we left off was the point that on the previous slide we established that these individual internal decisions they are organized by these bifurcation diagrams, and so the second idea I want to introduce is that once we have attention dynamics, these nonlinear decisions are can be controlled by and amplified by feedback. And so in this particular case, what this feedback accomplishes is it allows the agent to reject information below a certain threshold. So here, when it's receiving a smaller bias, here it's 0.5. The equilibria of the system are at the intersection of the null clines of the attention and the opinion dynamics, so the black curve and the red curve. So here, an agent that starts unopinionated remains close to neutral, but on the right, it's the same exact dynamic, but the agent receives a piece of bias that's a little bit stronger, so it judges the information to be sufficiently convincing and amplifies it, slides the attention along that unfolded bifurcation diagram and arrives at a much more decisive state than the bias itself. So this type of selective sensitivity that can then be tuned by the design of the feedback law, by the design of the shape of that red curve. This is what this framework enables us to do. So, of course, so far I've been talking about just one agent, and naturally moving to multiple agents, we have to introduce a social network. So when we talk about a social network, agents now are able to exchange beliefs with their neighbors, or at least estimate beliefs of their neighbors through some mechanism. I'm going to introduce also the potential for relationships on the network to be heterogeneous. So for example, you might have positive and negative links that correspond to cooperative or antagonistic social relationships. So the graph adjacency matrix might have signs. So once you have the social network, then accordingly, the belief updates or the opinion updates of the network should also reflect information or influence coming from their neighbors. And so in the multi-agent setting, we have the nonlinear opinion dynamics model that basically just adds the social information component to the nonlinear mechanism we saw on the previous slide. And similarly, when you have an unbiased set of agents, so if the biases are all 0 across the network, then in this model, the state of global indecision is always in equilibrium, and we can study its stability. And just like in the single agent case, we can find a bifurcation point where the state of indecision switches from being stable to being unstable. And so that bifurcation point is going to be modulated by network structure because it's going to depend on one of the eigenvalues, the maximal eigenvalue of our graph adjacency matrix. This bifurcation point corresponds exactly to that state of transition to a decision state in the network. But now, because we're talking about a group, we can relax a decision to be not only an agreement or consensus type decision, but disagreement, as I alluded to earlier. Things like task allocation are forms of desirable disagreement on the network that we want to be able to use these mechanisms for. And it turns out we can actually understand analytically both how both, at what bifurcation point are these global transitions triggered for sufficiently connected networks, but also what the pattern of resulting decisions looks like related to the graph structure. So here I'm showing you two different scenarios. So we have on the top here two graphs. So the color here reflects the opinion at equilibrium at one of these two decision states, decision 1 or decision 2. And so you can see the bistability on a cooperative network where all of the 8 edges are positive now corresponds to all agents choosing the same option, whether option 1 or option 2. But once we make some of the edges, or all of the edges in this case, negative, so we have a fully antagonistic network, then the state that emerges is actually heterogeneous, where the group splits up into 2 subgroups, some of whom choose option 1 or option 2, with the second decision state being the exact flip of that. And the pattern of these opinions, who has the strongest opinion, or how are the 2 subgroups split, the first order that's reflected by the leading right eigenvector of the adjacency matrix, and that's a consequence of center manifold theorem and how these bifurcations emerge on these nonlinear manifolds. So that's very convenient. But then the other thing that's really nice is that we get for free with this nonlinear opinion dynamic update is that also the biases, which are now heterogeneous and distributed on the network, now the biases are going to affect the global decision state. And how the biases affect the global decision is also something that can be understood through the network structure, because just like in the single agent case, we get this type of unfolded diagram where near the bifurcation point, whichever decision state is favored gets selected and becomes a unique equilibrium in this neighborhood. But which one is selected can now be understood based on the projection of the network biases onto the left eigenvector of the adjacency matrix. If the graph is symmetric, of course, the 2 coincide. But for directed graphs, the sensitivity eigenvector is going to be different than the critical eigenvector. So you might have agents who are very opinionated who are actually not as influential as others. So that's very nice. And that also implies that even if only one of the agents is receiving a piece of information or a bias, the entire group can react in this very sensitive way if it is strongly connected. And just like in the single agent case, this motivates us to design attention feedback laws to enable cascades of opinionation on the network in response to, for example, information coming in. So here in this simulation on the bottom left, we have a graph of 5 agents, and only one of them, this bottom one, receives a piece of information or a bias, say towards option 1 at time 20, which is indicated here by a dashed line. And with the attention feedback mechanism we've introduced, this one agent receiving a piece of information triggers the entire network to also ramp up their attention and slide through that bifurcation point in the opinion manifold and take on the decision that is favored. So it allows the entire group to amplify information received by one or a small number of agents. And all of these ideas can also be taken to beyond the binary decision to the multi-option setting. So in our work, we develop these models not just for the binary setting, but by considering agents that form beliefs on multiple topics, where now they have vectors of beliefs. The story gets a little bit more complicated because now there is multiple graphs you have to consider, and there can be inter-option coupling. The model becomes a little bit longer, you can see here on the top, but the story stays the same in terms of the math, if you understand the intuition behind these bifurcation diagrams. So long story short, whether you're thinking about a single agent decision, a binary decision, a multi-option decision, a network decision, these fast, flexible, tunably sensitive decisions, they're organized by bifurcations that can be controlled by feedback, and they're modulated by network structure, both in terms of where the decisions end up and how the influence across the network is distributed in terms of sensitivity to biases. And so in the last 10 minutes of this talk, what I want to do is highlight a couple of ways that these ideas are being used in practice. And the first thing I'm going to talk about is a project led by Shui Wang, who's my PhD student here at Cornell, in which we're using in collaboration with Eduardo Sebastian and Amanda Prof at Cambridge. We are using these bifurcation guided ideas to design control laws for navigation based on visual inputs in symmetric environments. And so, in particular, the setup we have is the following. What we're thinking about navigation, whether it is a mobile agent moving in 2 dimensions or in 3 dimensions, like drone flight. And the mobile agent that we're considering is equipped with a camera on board that has some limited field of view that can be subdivided into pixels. And we want to design a velocity controller that leverages this symmetry-breaking bifurcation mechanism and allows us to go to a target or a sequence of targets, so resolve that issue with symmetries that we saw earlier in the talk, where some of the classical approaches might get stuck. And furthermore, we want to do it based on solely camera input. And so the setup we have is the following. Where is the decision coming in? Well, the drone or the robot more broadly has to make a decision on an instantaneous decision on the direction of velocity at each step of its navigation. And so you can associate each pixel or each subgroup of pixels if we're downsampling with a unit vector, with an egocentric unit vector that points in a direction. Then we can process images like this camera view here on the bottom left, using some out-of-the-box vision algorithms, anything from masking to optical flow to pre-trained vision models. to evaluate which of the pixels contain information about targets. So this, unlike in the previous work that I talked about, was purely theory, where in this case, because we're thinking about options as individual pixels and the directions associated with them, how many actual spatial options there are is in this context, we're agnostic to that. And so where these nonlinear bifurcation type mechanisms come in is that now we're going to take the obtained pixel weights, and they're going to tune how much attention we're going to pay to each of the directions, the goal directions, and we're in a dynamic decision layer. And so to summarize the full setup is the following. So we have an autonomous robotic system, like a drone, from which with an onboard camera, from which we obtain an image. The image is processed, and then we have a dynamic vector field, like the opinion dynamics, or we're calling it neural dynamics here, where now the input is tuning. So this matrix here that it has the P and the D. The P contains the directional components. So those unit vectors that are not changing, but the D is coming from the vision is tuning that the attention to each of the pixels. And so after this stepping forward, this neural integration, we can then use after thresholding the unit or the vector of opinions or neural states to select which of the velocity directions are going to matter in terms of supplying a velocity command to our low-level controller. So this loop from vision to decision making back to low-level controller thrust commands is closed via this opinion dynamics controller. And we've tested this in a couple of different settings. So here, this is a trajectory from a photorealistic simulator in which there's a sequence of targets arranged. So the left-hand side is a simulation that Shuei ran that has targets arranged in 3 sequential steps. So the drone is moving from left to right. So at first, and on the right-hand side, the plot is showing you the top-down field of view. And so you can see that in the first stage of this process, the 2 targets that are the closest to the drone are arranged symmetrically. So this is very similar to that earlier setup that we had that proved to be a bit of a pathological example. And between these 2 symmetric targets, the drone makes a decision, visits 1, moves on. In the second stage of this, there is not much of a decision to be made. There is 1 target in the middle, and it can successfully visit that, center itself on that target. And then when it gets out here, there's 3 targets. So that's the third stage. And it can once again make a sequence of decisions and navigate to one of the targets. And is doing so with a pretty minimal computational burden, because there is no learning, no MPC, nothing like that involved. So it's actually quite light. Then another example that Shuei set up is in dynamic multi-target tracking. So this is a similar, this is the same simulator, but now there's a formation of 3 drones that the goal of our controller is to track one of these 3 drones, again, based just on vision inputs. And there's 3 stages to the behavior of the drones that we're tracking. So in the first stage, for the first amount of time, the 3 drones are flying in formation. And so during that stage, I forgot to mention in the previous example, the visual inputs were processed with using just simple masking, And here it's done using optical flow, which is why it's a little bit more jittery, because optical flow is a bit noisy, but regardless, you can see that there's 3 stages. At the first stage, 2 drones split from 1, and then at the last stage, the 2 also split. So there's 2 decision points that our control drone has to make. It has to choose at first, when the group splits, who do I follow, the left or do I follow the right? And it reliably chooses to follow the bigger group, which is nice and interpretable behavior. And then when the secondary point of the decision, it again is able to not get stuck in indecision and follow one of the drones. And we've also done some hardware experiments and this is about Eduardo, the work of Eduardo Sebastian in Cambridge. So you can see here on the left is the top-down view of the drone flying towards one of the 2 targets, and on the right it was the visual input it was getting. And in hardware, we can verify that this decision-making mechanism is in fact quite robust, and we're able to recover this binary splitting of being able to go both left to right and kind of break that deadlock. And one of the interesting things about this is actually it ended up being not on purpose, but kind of an illustration of how robust this type of a decision mechanism is, because as you can see on the top right here, that's the camera input we were getting. So one of the cables got a little bit disconnected during the experiments. So the visual input was actually quite noisy and unreliable, but despite that, this decision mechanism for generating velocity references has actually resulted in quite a robust adaptive controller that uses very minimal computational resources on board. And then I just have like 2 slides that I want to mention. So far I've talked about leveraging these bifurcation mechanisms in individual decisions. Another line of work I have in collaboration with Tyler Payne and Michael Benjamin at MIT is actually in incorporating this type of opinion dynamics and bifurcation-based logic into distributed teaming strategies. And so here, just a quick summary of some of the work that Tyler has led on this. You can imagine a hierarchical framework for multi-agent autonomy where there's multiple different types of decisions that agents have to make. So there's a collective decision, which is in this context, which team do I join? So different teams might be doing different tasks. And then there's local decisions, individual decisions that are actually about accomplishing the task and optimizing performance on that task. And so the opinion dynamics in this case is responsible for the group choice layer, where what we were calling the bias previously is now actually in feedback with the state of the agent and the state of other agents, and encodes the individual utility with respect to that task. And just to show you a couple of videos that Tyler has hopefully shared with me. Again, the big picture here is just that in different scenarios. So here, this type of hierarchical framework with opinion dynamics was set up for this to help a team play an autonomous capture the flag game, where agents have to decide whether they're going to protect the flag or attack the flag of the opposite team. And so you can see at the bottom, the opinion of the 3 agents is being tracked. So like what they are doing, which team they're joining, what strategy they're deploying. And you can see this type of controller can lead to very sensitive and adaptive teaming that's responsive to very fast changes in the strategy of the opponent. So those are just two examples. There's a lot of other work that's, for example, incorporating these types of ideas into safety control and other exciting applications. And so, yeah, thanks again for the invitation. That's all I had. And please don't hesitate to reach out. And if you're interested in these ideas, yeah, check out my new group at Cornell. I just started here last year, so we're hopefully going to get a lot of exciting things off the ground soon. So.
Thanks so much, Anastasia. There's a confluence of clapping, virtual clapping here. Let's open the stage for questions. You can either raise your hand or just type in the chat. And I see Kathy appearing, so I expect a question from Kathy.
Thanks so much for the amazing talk. So I'm actually asking the question on behalf of my lab mates who needs to leave early. So the question is, how does this relate to chaos and nonlinear dynamic systems with bifurcation?
Yeah, so the system, so the opinion dynamics system is a nonlinear dynamical system that exhibits a bifurcation, right? So chaos is a type of behavior that can happen in nonlinear dynamical systems. So we're not operating the opinion dynamics in a chaotic regime. So the idea is that we have a much more nice low-dimensional bifurcation whose states are interpretable with respect to like a desired design objective in our system. So so we're specifically utilizing that property in order to in order to get all these nice outcomes in the decision process that I've described in the talk. Hopefully
Thank you. And can I ask one question for myself?
Yeah.
Because you mentioned like in terms of, I guess, breaking the tie involves like, it's also important when you solve like say for multi-agent path planning, you can have deadlocks with a safety filter. I was wondering like, is it possible to use some of these stuffs to resolve the deadlocks, specifically say with a control barrier function, and also and this is in the setting where you have like somehow like symmetry tie breaking, right? But in some sense, it's actually for the deadlocks, there might be like you can assign different priorities and things you can have different level of optimality by how you assign the priority, and you don't even know at first hand like what should be your bias or what should be the priority. Can you elaborate on in that sense? Do you have any thoughts on how we should solve problems like this?
Yeah, so I guess the first thing you said was about the safety filters. So yeah, actually I wanted to highlight there actually has been several works that in all I think that came out in the past year that have incorporated this opinion dynamics framework into various types of safety filters. So in fact, actually, our collaborator on this work, Eduardo, who was here on this slide. So Eduardo Sebastian, he actually co-led a paper that just appeared in RSS that is about combining opinion dynamics with velocity obstacles. And then there was two papers that I saw recently that I think at the moment are preprints. Or actually, one of them might be already published. One of them I think was in the European Control Conference, and one is a preprint. I guess the name of the authors escaped me, but one combined these symmetry breaking ideas to resolve line locks in airplane safety, airplane control, and then one was the one at the European Control Conference last year was specifically about control barrier functions and synthesizing this with control barrier functions. So I'm happy to share these papers with you if you shoot me a message or an email. And I just don't remember off the top of my head what the names are of the authors. And then the second question was what happens when you don't know the bias a priori, right? And I think that's part of what we're getting at, I think, with this last part that I really sped through. So the biases are static in the analysis that I showed just to emphasize the role of bifurcation, right? Because once you make the biases dynamic, you have an entirely different dynamical system. But in practice, you can understand, like, once you have biases that are maybe learned or dynamic. You can still understand the emergent decision behavior with respect to the manifolds induced by the opinion dynamics, especially if there is, for example, a time scale separation. You have slow fast dynamics where then the decision is going to be closely tracking the manifolds induced by the bifurcation structure of the opinion dynamics. So so in practice, like in like the application towards the end here, the biases in this autonomous teaming case, right? These were not static biases that are known a priori. So you can think of this entire like in the individual utility function as a bias, right? And so here, I was not very clear. So here the states Z are the opinions, but states X are actually like physical variables of the robot, right? So that's then I guess one of the one of the
biases are somehow kind of like learned through some
yeah. Either learn. But I don't think there was learning specifically in the example that I showed you. But yeah, they adapt to some. They're in some feedback with the environment, and there are. I think there are some examples where people have done some things with learning as well. I also had some work a couple of years ago where we were thinking about games, in particular social dilemma games. And in that case, the biases were actually coming from like a game theoretic payoff structure as well, right? So you can so the whole idea is very much that like you can structure how these biases come in differently depending on your application. And so I think there is not currently like a cohesive feedback theory between like what happens when you interconnect this bifurcation diagram to biases. Is something I'm super interested in. And I think it's a big open question. I think traditionally a lot of bifurcation theoretic work has been done in communities that don't think about inputs in the way that maybe control theorists think about inputs. So I think there's a lot of opportunity to connect these two things. And so I think this work is meant to push things in that direction in some way. Yeah.
Sounds very cool. And I'll send an email to follow up.
Thanks so much, Kathy, for the nice questions. I don't see any other questions. I think you can reach out to Anastasia. You had your email on the last slide, right? So
yeah,
we will reach out. Thanks again for the great talk and looking forward to catching up soon.
Thank you.
Take care.